I'm going to talk about impact of our work, complexity, and obstacles that we face, and what is important for building better distributed systems, especially when other life-critical areas rely on and build on what we create. We're going to look at some fundamental techniques and concepts used by real systems. Many systems available today already offer many solutions. They encapsulate a lot of distributed algorithms. They automate and abstract away a lot of the complexity. And engineers who rely on those systems don't necessarily have to have the same massive amount of knowledge that was required to build them in the first place. So even though there is less and less necessity for new engineers to learn the fundamentals, in some situations, knowing what's behind the scenes could be essential for making the right decisions and for solving difficult issues that come up when something doesn't act as expected. So why is it important to come back to fundamentals all the way from where we're now? We're at the point where distributed systems get increasing adoption in the medical field, in transport automation, autonomous devices, and many other life-critical areas where the cost of mistake is growing, and correctness becomes really important. Cost of mistake is not necessarily how many seconds your system was unavailable today. It's more about what was the price of your system's failure to your users and to their users. I think we should take it with responsibility and always try to remember why we're doing this and what is the real problem we're solving. Every industry wants to make more progress by combining their and our research and solutions. Our work helps other fields and domains to be better at achieving their goals. And it can be immensely useful for us to understand how to relax certain limitations and how to fine-tune certain trade-offs. So understanding what's at the core can be a powerful tool to navigate the complexity of ever-changing options and tools. And it can help us create correct solutions for improving the options we have. But it turns out it's not easy, and there are some obstacles in our way. Sometimes it's challenging to understand what correct means for our systems. There's a big gap between theory and practice. A lot of theoretical material is not approachable enough, and it's notoriously hard to grasp. So it often doesn't include information necessary to turn this theory into practice. And production systems have to modify the theoretical algorithms and adjust them for practical environments. And many of them don't reveal the specific details important for practical solutions. And even a slight misunderstanding of specific details of a protocol can completely destroy its correctness. So we need to do additional work to make sure that our systems are correct in reality. It is challenging to verify and maintain correctness of distributed systems in real-world environments. It could sound perfect on the paper, but be inefficient or hard in practice. It could sound unrealistic in theory, but be perfectly acceptable in practice. There are too many things that can go wrong, both in the algorithm logic and in the implementation itself. On the other hand, correctness is not always a priority. There are always deadlines, competition, customers who want their solutions faster. And it can happen that the system will be rushed and not properly correct. That means that a team might not have time to properly discuss and systematically address the real reasons behind the rare intermittent issues, which will happen again and will lead to more of them in the future. So how can we be better at this? We can improve in many directions. One of them is emphasizing and putting more focused efforts into improving correctness to make sure that our systems keep doing exactly what we expect them to do. Another one is improving understanding of how they work, which helps reduce the complexity and possible mistakes, and helps us face the challenges that come up. When we aren't implementing distributed algorithms and concepts directly, we definitely rely on systems that do. And at the point where our work is integrating into other fields and domains, understanding fundamentals and trade-offs becomes extremely relevant. If you're promised a certain level of performance or consistency, how do you actually make sure that those guarantees are provided at the exact level you need? It's hard because when several computers are talking to each other, trivial problems become hard and they accumulate. Distributed systems are hard to understand, hard to implement, and it's hard to keep them correct in practice. I think there are many ways to show why, and I recently had a chance to explain it to someone from the field of bioinformatics who was wondering why they needed to make trade-offs between important system properties in distributed setting. So the first thing that came to my mind was ordering. Ordering is easy on a single machine, but when messages are sent across network, we can't really rely on physical timestamps, because physical clock on different machines, they tend to drift. So in distributed systems, we often apply logical clock, or simply speaking, just counters that are being passed around between nodes. But because of asynchronous nature of our environments, there isn't an easy way to establish complete ordering between all of the events, because some of them are concurrent. So what we can do is figure out which events are really concurrent and which of them happened one before another. So with even such a simple task, we already have to make some decisions. For example, would it be OK if a system told us that events are ordered, but in reality, they turned out to be concurrent? Or do we need to know for sure that events are not concurrent when we can't simply order them? We can't simply order concurrent events, and sometimes we still need to make decisions on the order of operations, on a value, on a sequence of values, or anything else. And it turns out that getting several machines to agree on the same thing is another scenario where we have to ask ourselves questions and make some choices to determine what's right for us. For example, two-phase commit is one of the solutions that can help all the nodes to agree on something. And it works as long as they don't fail. If some of them crash, then to prevent any possibility of inconsistent data in the system, the algorithm just blocks until the crashed nodes come back, which might never happen or take a really, really long time. So the algorithm is safe, but it isn't live. What if it's not something we can accept? Sometimes we really need the system to respond. In this case, we might have another possible solution, three-phase commit, which doesn't block when there are node crashes. But if there is a network partition, then the two isolated sides of the network can come to two different decisions after they time out, and the system will end up in an inconsistent state. So here we have the opposite problem, where the system is responsive and live, but it's not safe because different nodes can decide on different values. If we are OK with any of these two options, that's great. But what should we do if we really want our data to be always consistent and the system to be responsive? Well, we can discover some news. Precisely an impossibility result that proved that actually there isn't a deterministic algorithm that would always come to a decision and terminate in a fully asynchronous system with even one possible failure. The main thing we can learn from this is that if we really want to solve distributed agreement in practice, we will have to change our assumptions and rethink them to reflect more realistic expectations. For example, we can put an upper bound on the maximum message delays, or we can determine what is an acceptable number of failures for our system. And if we do change our assumptions, then we can solve distributed agreement in multiple ways. I think the most famous solution that is very classic is Paxos. It is known to be hard to understand and hard to implement. It actually works, and it does provide safety and liveness, but only under condition that the majority of nodes need to be up and that we put an upper bound on maximum message delays. So in Paxos, any node can propose any value, And after going through a prepare and propose phases, all the nodes should agree on the same value. And there is a requirement that the majority of nodes need to be up so that all the quorums intersect, so that at any point of time there is a node that is aware of the most recent proposal to make sure that we're never agreeing on older, outdated values. There are many possible optimizations to the initial algorithm that make it more efficient in practice. There are also many possible variations to the consensus algorithms based on the trade-offs they choose. For example, how much work is done by leader? Having a strong leader could be good or bad, depending on how frequently it fails and how hard it is to re-elect. Another trade-off is how many failures we can forgive and how large our quorum size should be. Another somewhat underrated criteria is how understandable and implementable the algorithm is in practice. For example, Raft is popular because it was much more understandable, and now it's applied in many widely used projects. But what's even more interesting is that even the topic of consensus and agreement isn't new at all. We are still discovering new trade-offs and optimizations. For example, in classic Paxos, all the quorums need to intersect, and the majority of nodes need to be up. But it turns out that we can rethink how we work with quorums, and we can simplify the majority quorum requirement. It turns out that it's only enough for the quorums of prepare and propose phases to intersect, which opens up a lot of doors to us and gives us a lot more flexibility to experiment with quorum sizes between different phases. So it's very useful in practice. The main point is that up till this day, we're still discovering new performance and availability trade-offs. And it really helps us expand the spectrum of choices that we have. So consensus is just a building block that is used in many other areas, like distributed locks, replication, and many more. Speaking of replication, we can actually use consensus to implement strongly consistent replication. But one of the downsides here is performance. The other side of the spectrum is, of course, eventually consistent replication, which is very fast, but then the client can get inconsistent data as a result. Usually, we want to get some better performance and still maintain stronger consistency. So in some cases, we can actually come up with solutions that are faster than consensus, but provide better consistency than just eventual. One of the interesting examples here is Aurora, where they avoid consensus for I/O operations and a couple of other operations. They use quorums for writes. They don't use them for reads. So in reality, their replicas might be storing different values. But when the client performs a read, the database, because the database maintains certain consistency points, it is aware of the nodes with the most recent consistent data. So the client always gets consistent data as a result. Another interesting example is conflict-free replicated data types. They provide strong eventual consistency, so both fast reads and writes, and they stay available during network partitions. And this is without using consensus and without using any synchronization. However, this is only possible if we can have rules for resolving any conflict with concurrent updates. In other words, we can use this technique only if we can define a special merge function for concurrent updates that can apply them in any order as many times as we want without corrupting the result. So this is a perfectly acceptable example where the updates are additive, and this technique can work. This one, on the other hand, isn't as obvious. We don't have clear rules for resolving this concurrent update conflict, so we might not be able to use it here. Azure Cosmos DB uses CRDTs for conflict resolution for multi-region, multi-master writes, and Redis and React also use CRDTs as well. So if we teleport into a completely different area in distributed systems, we will always find more trade-offs. For example, failure detectors. They are very frequently used for discovering node crashes and applied in other areas like leader election, group membership protocols, and other areas. We can measure their efficiency by looking at their completeness and accuracy properties, where completeness tells us whether some or all of the nodes can discover all the failures. And accuracy measures how big of a mistake a failure detector can make in suspecting a failure of another node. So it turns out that even unreliable failure detectors can be really useful in practical systems, because we can turn any weakly complete failure detector into a strongly complete failure detector by adding an additional gossiping mechanism that would spread the knowledge of failures to all of the nodes. So why should all of this matter to us? Trade-offs take different shapes and forms, and we can be really flexible if we know where to look and how to use them. Many products are built around distributed algorithms and trade-offs. And these products make certain choices for us. When we use products, we make certain choices as well. So uneducated choices can lead to delays and data loss. For some systems, this can mean losing clients or large amounts of money. For other systems, this could result in slow reaction, a wrong order of actions, which could pose an actual life threat. So understanding fundamentals and concepts is really important for making the right choices, for knowing what correct means for us, and for maintaining correctness in real life. So after we're clear with our decisions and trade-offs, how do we actually maintain correctness in real systems? One of the frequently used techniques is system model checking. Model checking is useful because we can explore all the possible states our system can end up in. And there are quite a few tools out there. For example, TLA Plus is pretty popular. And there are many other emerging techniques like semantic-aware model checking. But if we're talking about verifying correctness of real running implementations of distributed systems, model checking alone isn't enough. Not many projects actually publish information about how they verify correctness of their systems and test them in real environments, but actually some of them do. For example, Kafka has a variety of system tests run every day, and anyone in the world can actually look at it and look at what components are working as expected and which one don't. So Cassandra has a really great write-up about their approach to comprehensive testing. And I really wish more projects and products and systems would be more transparent about the efforts they put into verifying their systems. But if we look at what it takes to be prepared to run a production-ready distributed system, there's quite a lot. Of course, we can use unit testing and integration testing for small-scope tasks and for making sure that multiple components work together really well. But it's not enough, and there are more techniques that we can use. For example, property-based testing and fuzzing could be really useful to provide randomly generated input into your system and make sure that its fundamental properties are correct based on its specification. I actually worked on a fuzzing project at Microsoft Research, and it's a really fascinating area. There's also performance testing and fault injection if we want to make sure that the system is available during specific fault scenarios and to verify that the expected properties remain correct. With all of that, a crazy amount of reasons behind critical errors is actually because of incorrect exception handling logic. So there are definitely some things that we can fix, but we can't fix all of it, because we are humans. It's impossible to know every single thing. There are too many components. We would never discover new ground. We would never learn anything new if we were afraid to leave the area we're familiar with. But what we can do is we can prepare ourselves better for dealing with unexpected errors. We can find patterns and try to address what causes them. That's why knowing the state of your system really matters, and observability matters. So it's much less scary if we are aware of the possibility and are ready to solve those production errors. So what are some of the takeaways? Products change really fast, and the terms that describe their consistency, performance, resiliency, they are extremely overloaded. Fundamentals and trade-offs, they stay and they build up. In isolation, they're not very useful, but knowing them can be essential for making the right choices and maintaining correctness in practice. And correctness is especially important when our systems are trusted in scenarios where a certain level of responsiveness and safety is a strong requirement. If you're building something, ask yourself a question: can this be misunderstood? Because misunderstanding creates complexity. And complexity is like a big bulletproof wall around your project that makes it hard to explain, hard to use, and hard to improve. So try to build understandable systems, because understanding directly contributes to correctness. Correctness is not easy, and it doesn't come for free. We have to work on it and make it a priority, not just at the level of one engineer willing to do it, but at the level of your entire team or an organization. Don't just trust your systems to work, test them and verify them, and show your users and customers what efforts you put into verifying your systems. And one last thing, there are many of you here from different areas within the field of distributed systems. So think of areas related to your work that are important, but that don't get enough attention. If you ever have an opportunity to chat with people different than you who work in other areas, do it and ask them questions about what challenges they're facing, what trade-offs they're making, because it will help you be a better engineer. Thank you.